Clustering is a set of unsupervised methods for grouping data according to certain criteria into so-called clusters, which allows you to identify similarities and differences between objects, as well as simplify their analysis and visualization. Because of the partial similarity in the formulation of tasks with classification, clustering is also called unsupervised classification. Clustering is widely used in machine learning to solve a variety of tasks. For instance, in market segmentation, clustering helps divide potential customers into groups based on their characteristics to develop more effective marketing and sales strategies. In medicine, clustering is used for grouping symptoms, diseases, and drugs to enhance diagnosis and treatment plans. There are many different types of clustering, which can be divided according to the following criteria: partitioning, density, grid, and model-based. In some cases, while analyzing data, you might realize you know little about it, but want to understand its homogeneity, or whether it can be divided into groups. Such groups can be called clusters. In other words, we are trying to find patterns in the data itself without being influenced by any specific desired outcomes. First of all, we should start by discussing the essence of the K-means model, which is one of the simplest clustering methods. The essence of this method is to find a given number of clusters K and their centers, so-called centroids, such that the distance from the centroids to all points of the cluster is minimal. K-means groups similar elements into K clusters, with K being any integer value. For example, if we have data with two attributes, the K-means clustering model can divide them into segments. The core idea of K-means is to find the centroid, which is the average value of our clusters around which points will be clustered. This model works better with spherical clusters. If your data has a more complex structure, you should consider using another clustering model, as K-means may not perform well in such cases. Now it is time to embark on our journey, engaging with practical environments, and getting intimately familiar with algorithm. Before we implement our machine learning model, we need to import essential libraries in Python: NumPy for numerical operations, Pandas for data manipulation, Matplotlib for visualization. These libraries enable us to handle data effectively, visualize insights, and generate synthetic datasets for testing our models. For effective visualization of clustering datasets, utilizing the plot data function enhances our ability to explore and understand data distributions and class separations visually. By specifying parameters such as marker type, colors for class differentiation, transparency, and marker size, this function aids in insightful data exploration prior to applying machine learning algorithms. Next, we will introduce a function that generates synthetic datasets for special tasks based on specified methods like linearly separable data, moon-shaped data, or concentric circle data. It allows control over parameters such as the number of samples, noise level, and random seed for reproducibility. This flexibility enables the creation of diverse datasets tailored for testing and evaluating machine learning model. In the accompanying code, datasets with 150 samples and a noise level of 0.15 are generated using this function. The results are visualized across 3 subplots, showcasing the distinct characteristics of linearly separable data, yin-yang shaped data, and concentric circles. This line of code generates a binary separable dataset with 150 samples, using the line linear separator method, and adds noise with a standard deviation of 0.05 to the features. To start with the K-means algorithm, let's understand the basic methods for distance calculation used in machine learning. It is often crucial to quantify the dissimilarity or similarity between data points, vectors, or matrices using specific distance metrics. These metrics help in various tasks such as clustering, classification, and regression. To facilitate this, a distance function has been implemented to calculate distances between two vectors or matrices. This function calculates the distance between two vectors using different metrics. The function takes in 3 parameters: x1 and x2. These are the 2 vectors for which the distance is to be calculated. Next, metric parametres. This specifies the type of distance metric. The available options are Euclidean distance, Manhattan, Chebyshev, and Minkowski distance. And last, parameter p. This is a parameter for the Minkowski distance. If the metric is Minkowski, this parameter determines the degree of the Minkowski distance. The K-means algorithm starts by selecting random data points as initial cluster centers, called centroids. These centroids act as seeds for the clustering process. Then, it calculates the distance between each data point and all the centroids. Each data point is assigned to the cluster with the closest centroid, forming a preliminary grouping of the data. However, these initial centroids might not be optimal. To refine the clusters, K-means recomputes the centroids by taking the average of all points belonging to each cluster. This essentially repositions the centroids to be more representative of the actual cluster centers. The process of calculating distances, assigning points, and updating centroids iterates until the centroids no longer significantly change, signifying that the clustering has converged. Before embarking on clustering, it is essential to initialize the cluster centers. To achieve this, we randomly select indices among the available ones in the dataset. This process is crucial for determining the starting point of our clustering algorithm. Let's illustrate this concept by performing a simple two-cluster clustering. We begin by taking each centroid and calculating the distance from it to all records in the dataset. The value indices for each cluster are chosen as the indices of minimum distances to the corresponding centroid. Consequently, the zero cluster will include those points in the dataset where the distance to the zero centroid is less than to the first centroid. To visualize the result of this initial clustering, we can create a function that generates initial centroids, estimates cluster labels for these centroids, and displays the outcome. Next, we select new centroids as the midpoint of each cluster. To accomplish this, we need to identify each cluster individually and calculate its midpoint. The new centroids are then used to recalculate the cluster labels and visualize the result. To demonstrate both old and new centroids, we can display them side by side. Now, let's calculate the relative distance between old and new centroids. If the distance between the updated centroids is relatively small, indicating that they have stopped changing position, we consider the clustering to be complete. To automate this process, we can implement an iterative clustering procedure. At the end of each iteration, we output the resulting iteration number and the distance between clusters. Finally, we can check and visualize the results to ensure that our clustering algorithm has converged successfully. As usual, we'll combine all our work into one class. Having built our K-centers clustering class, let's put it to the test. We'll determine the optimal number of clusters using the elbow method. This technique involves running K-centers with various K values and plotting the resulting distortion, variation within clusters against K. The ideal K often appears as an elbow on the graph, where the decrease in distortion plateaus. We'll delve deeper into the elbow method for choosing the optimal number of clusters in a later video. Finally, plot the elbow graph, showing the sharpest drop in spread at 2 or 3 clusters, where the within-cluster distance decreases rapidly, indicating the optimal number of clusters. First, we'll create a K-centers model object and train it with K equals 2. While 2 clusters might seem intuitive, the elbow method will reveal the true story. We'll then visualize these clusters to see their distribution. Next, we'll explore K equals 4 clusters. Visualization becomes especially important here. By comparing the K equals 2 and K equals 4 clusterings, we might visually identify that forcing 4 clusters creates unnatural separations within the data, suggesting a different optimal number of clusters. Before diving into evaluation metrics, we need to understand how cluster labels are distributed. The pandas crosstab function from the pandas library comes in handy for this. We'll create a data between the true labels if available and the cluster labels assigned by our K-centers model. This data can reveal interesting relationships, like the potential merging of clusters based on their label distribution. This analysis paves the way for further evaluation. Now we will discuss the K-means algorithm problem. For this purpose, we will generate different data. To build a K-means model, we need to determine the number of clusters. Initially, these centroids poorly describe our 3 article segments, but we need to determine which cluster each point belongs to. Then, we recalculate the centroid, shifting it to the center of popularity by averaging all points in the cluster, and during the training process, they will move and find the optimal centers of the clusters. We get new centroids marked with black bordered stars, which are still not in the right places. We see that our solution is not optimal. We wanted different cluster divisions. But this is what we got. We can only try a new random initialization of the starting centroids. If we're lucky, our centroids will end up in different point clouds. Instead of relying on luck, we can use a more intelligent method for centroid initialization, K-means. This method initializes centroids more intelligently. In short, it chooses the most distant points from each other as centroids to ensure they don't end up in the same point cloud. Let's detail the possible implementation of K-means++. First, generate a random point as the first centroid, marked with a green star. Then, for all points, calculate the distance to this centroid, and choose the point with the largest distance as the next centroid, also marked with a green star. Now we have 2 centroids, we need a third one. For each point, calculate the distances to both centroids and choose the minimum distance the closest centroid. Then, for another point, do the same. calculating the distances and finding the minimum. Repeat this for all points, find the minimum distance for each, and choose the point with the largest minimum distance as the third centroid. This logic finds the most distant point from the existing centroids, which will be our third centroid. This is how the K-means++ initialization looks like, with points lying in different segments or clouds, maximally distant from each other. Now start the K-means training cycle, which yields excellent results. Finally, discuss how to choose the optimal number of clusters. To build a K-means model, we must determine the number of clusters beforehand. There are several ways to do this. The first way is to visualize the data and count the number of segments we observe. We now have a function for K-means++ initialization, which takes data, the number of clusters and randomness as inputs, selects a random initial point, and iterates through the data points to find the most distant points as new centroids. We visualize each step to see the progression of centroid selection. Let's now combine our K-means++ initialization with the K-means training function. This ensures that the initial centroids are well spaced, leading to better clustering results. The clustering results are visually much better, with clearly defined clusters. This concludes our session on K-means++ initialization. We discussed the problem of random initialization, implemented a method for selecting the most distant points as initial centroids, and explored the K-means++ method from the original paper. In the world clustering, evaluating the quality of the formed clusters is crucial. Clustering metrics can be broadly categorized into internal and external evaluation metrics. These metrics help assess the quality of clustering results based on different criteria. Internal metrics evaluate the quality of the clustering without reference to external information or ground truth. These metrics focus on the data's intrinsic properties and how well the clustering algorithm captures these properties. A common internal metric is inertia, which measures the sum of squared distances between each data point and its assigned centroid. Lower inertia indicates tighter clusters. Other internal metrics include the silhouette coefficient. A high value indicates that the point is well matched to its cluster and poorly matched to neighboring clusters. A negative value indicates that the point might be better assigned to a different cluster. External metrics evaluate the quality of the clustering by comparing it to a ground truth or known class assignments. These metrics assess how well the clustering results match predefined labels. Ultimately, a combination of internal and external metrics, along with visual inspection of the clusters, can provide a more comprehensive understanding of the quality and effectiveness of the K-means clustering process. This concludes our session. In this video we learned about the K-means model, an unsupervised clustering model that finds centroids, the centers of point clouds, dividing data into similar segments. We also learned how K-means is trained iteratively, choosing the number of clusters and initializing centroids, possibly using K-means++ for better results. Thank you for your attention, and I wish you great success in studying machine learning. Goodbye.